Hello everybody. In the last class, we saw how to design a static CMOS circuits. In this class, we are going to take on a design of dynamic CMOS circuits. Look. So before that, we start with what are the disadvantages with the static CMOS design, which has necessitated this new design called dynamic CMOS. So in the static CMOS design, suppose we need to implement an 4 input on an OR gate. So this is being implemented here in this circuit. You will see that all the PMOS they generally have to be scaled up in width so that the propagation delays are corresponding, and the rise time and the fall time to keep them close to each other. We know because of the poor mobility of the PMOS, those PMOS devices requires to be of greater width, right? So you will see 4 micrometer, all these PMOS devices are of large dimension ones, right? So so what happens because of this large dimension PMOS is the area will be large. So in the silicon chip layout, so area is also one of the constraints. So you will find it is going to take more chip area, consume more chip area, the static CMOS designs. Okay. The next one is static dissipation. Since we have an PMOS with the large width, so you will find there is a possibility of a greater static dissipation in all these CMOS circuits. Okay, because there is here, if you see, there are 2 parallel paths available here in this particular NAND gate. Okay, wherein from the VDD to here, from the VDD to here, so static currents can come like this, and then it can flow like this, right? So the static dissipation is an issue with the static CMOS designs. So with the higher technology nodes, that is as we keep decreasing the channel length, and the static dissipation keeps increasing. That we have learned in our first class itself. And then because of the high capacitances associated with this PMOS, the switching losses will be high. So we have learned the formula for power dissipation, right? And a VDD square CL into F. So that CL. So these PMOS, they contribute large CL with this large area. So switching losses will be high. On also the short circuit current. Short circuit current is when you have the input going from low to high or high to high, you will find a direct path between VDD and ground. So these are all the some of the disadvantages of the static CMOS. So to overcome these shortcomings, we have something known as dynamic. So this is another example of static full adder which we implemented in the last class, where you will see this entire top thing is known as the the PMOS pull-up network. So here also you have a large pull-up network. So all these pull-up networks of this, if you have 1, 2, 3, 4, 5, so you will find they are going to add capacitance. There are 2 parallel paths for short circuit current, and all these issues are there. Here also you will find that there are parallel paths available for static current dissipation, also for the short circuit. The switching capacitance also is higher in these circuits because of this large width. And we have seen that sizing of these transistors also in the previous class, where you need to scale up these size of these PMOS so that the rise time is well within the limits. So you will find this is a problem with the static CMOS. So now we have something known as dynamic logic. Okay, now what it does is now the entire P network is replaced by a single PMOS. Okay, and below the NMOS network, okay, you have one clock enable NMOS out here. So this is this example is specifically for a NAND gate. So in a NAND gate, you will have 2 PMOS in parallel. Now, so we just have a single PMOS. So irrespective of how big the PMOS network is, in the dynamic logic, we just have a single PMOS of a very small, the minimum width PMOS also we can use out here, and then you have an NMOS here onto which the clock signal is given. Here also we are going to give the clock signal. So how does this function is? So initially when the clock is 0, okay, when the clock is 0, this NMOS will be switched off. So when this if clock is 0, this PMOS will be switched on. So this output node will be charged to 1. So if you see here, this is the phi indicates the clock and y indicates the output. When the clock is low, you will find output is charged to high. Okay. Now since there is no issue because with the rise time, because it is pre-charged to 1, so it is slowly. So this PMOS can be of the least possible width also. So you don't have to have a PMOS which will have needs to provide high currents and needs to have high width. We can have a minimum width PMOS also, because there is adequate time available, right? When the clock is 0, the whole duration is available, clock duration is available, where this output can be slowly charged and kept pre-charged. It can be pre-charged to 1. Okay, and when the clock is going high, that is the time we are going to evaluate the output. Okay, so whenever the clock is low, if you see the output, it will be 1. Okay, whenever the clock is going high, this PMOS is switched off, because now the clock is going high. This is a PMOS, so you're getting a high signal here, so this gets switched off and this gets switched on. Now the output, whether it will remain high or not, it depends on the inputs. Okay, now if you see here, it is a NAND gate, so if both are 1, then this will go to 0. If either of them is 1, is 0, then there is no path available for this charge to get discharged, right? So it will continue to remain 1. So this will act like a NAND gate. Okay, so during the evaluation phase, that is during the evaluation phase, when the clock is high, okay, if both are 1, then this will be 0, and if any one of them is 0, then there is no path available for this charge to get discharged, and hence it will remain 1. So this is how a dynamic logic looks like. Okay, so you will see that so the entire P network is removed out here. Okay, so we'll take a few other but this also has gotten certain small issues, like, so one example is shown here. Now the dynamic logic suffers from something known as a charge sharing phenomena. Okay, that means now when the clock is low, this output is charged to VDD. Okay, say I call it as if this capacitance, node capacitance is Cy, and now suppose when the clock is going high, A is 1 and B is 0. So in that case, the output is supposed to remain 1. But what happens is, since A is conducting here, okay, and if we call this node capacitance as Cx, so this won't remain VDD. Some charge from here will come and get deposited here. So the net VDD, it will not be VDD here. So it will be VDD Cy Ca divided by Cx plus Cy. So this is known as charge sharing. So this is one small drawback of the dynamic logic. Okay, that is, whenever the clock is 0, the output will get charged to VDD. That is fine. Whenever the clock, and then when the clock is low, this is again the same NAND example. Suppose A is 0, B is equal to 1, then nothing happens because A is off. So this charge will be retained here. Now A is 1 and B is 0. Even in that case, we are supposed to have 1 out here, but it doesn't remain 1 here. It doesn't go to 0 also, but then it won't remain VDD also. So the VDD will fall below the prescribed limits because of this charge sharing phenomena. So this some charge, because A is on, will come to Cx, and this is given by this formula. So this is one small issue with the dynamic logic. Okay, the second issue is we can't cascade two dynamic gates. Okay, cascading is one dynamic gate is suppose if it is driving another dynamic gate. So now if you see here, this when the clock is low, this output will be 1 here, and this clock is low, this output also will be high. So if you see, when the clock is low, output 1 is high and output 2 is high. Now what is happening is the input has gone high here. So if this is high, this is an inverter, two inverters which are cascaded, dynamic inverters. So when this input is high, this should be high, this should be low, this should again be high. Okay, now what happens is, when the clock is going high, okay, this output is initially high. Okay, since it is initially high, the moment a clock is going high, this output will start discharging like this. Okay, so if you see here, out 1 is it is already, and it will start discharging. There will be some propagation delay, like, because this is now high, so this will go low after a certain duration, okay, and then it will switch off this transistor. So for that transient period, this output will drop from VDD. So that is another issue. Okay, if I repeat it once again, like this clock is going to be initially when the clock is 0, this is off, this is off, both these this is one dynamic inverter driving another inverter. Okay, so when the clock is high, this output node is 1, this output node 2 is also 1. Okay, when the clock is going high, so this is 1, so this should be 0, this should be 1, right? But this is 0, this is 0, and this is 1, but this becomes 0 only after a certain propagation delay, right? Because you are giving an input here, so this will take time for it to get discharged. So meanwhile, since it is 1 here, this also will start conducting, okay, and hence the output will fall below. So that is the reason you can't cascade dynamic gates. Okay, so that is an issue with these are the two issues with dynamic gate. So to overcome these issues, we modify the dynamic gates, and now we have something known as domino logic. Okay, in this two things we do. One is this is the output, right? If you take the output and you put an inverter and you put a weak PMOS, and a weak PMOS means whose either the width is too small or the length is very large. Okay, so what happens is whenever this is 1 out here, okay, whenever the output is 1 out here, when the clock is high, so if it is 1 here, it will be a 0 here, and if it is 0 here, this PMOS will be on. So for conditions where the output requires to be 1, so you have a feedback path, so this will restore the charge back to VDD. So if I go back to this slide here, now this is supposed to be 1, so you are taking one inverter and putting one more PMOS. So whenever this is 1 here, some charge keeps coming to this node, but that will be replenished by a feedback network here, because this is 1, there is one more inverter here and a PMOS here. So this output, this whatever charge distribution happens, that gets replenished by this. So that is known as a keeper PMOS here. So this has to be a weak PMOS, otherwise there will be some contention and there will be some short circuit current. So this we keep it very weak. The only purpose of this PMOS is because of charge sharing, a little bit charge gets from here, it gets shared here, so that needs to be restored back. So that is why you take one here, you put an inverter and you put a weak PMOS. So that takes care of one issue, which is charge sharing. And then you put one more inverter on top of here. So now if you see, when the clock is low, this node gets charged to 1 and this gets charged to 0, and then whenever you have the clock coming in, so either this will remain 1 or 0 and you get an inverted output out here. Okay, so now the basic difference putting this inverter out here by putting one more inverter out here is now during the pre-charge period, that is when the clock is 0, this node will be charged to 1 and this will be charged to 0. So what is the advantage of putting these two inverters is, if you see here, now you can easily cascade these two structures. So now if you see here, this is during the clock phase, this will be charged to 1, this will be charged to 0. If this is 0, and now what is this is going to be charged to 1, again pre-charged to 1. Okay, and then this will be pre-charged to 0. Now this node is going to be pre-charged to 1, this is going to be pre-charged to 0 because you have put an inverter. Now when the clock is going high, right, so this doesn't conduct because this node is pre-charged to 0, right? So it is not immediately going to conduct. So this will continue to remain 1 here. Now what happens is, depending on this input, whether it is high or low, this output will continue to remain 1 or it will go to 0. So if it goes to 0, then this will go to 1. If this is going to 1, then this will become 0, and this is going to 0, then this will go to 1. So you will find so only in that condition. So this is not going to the moment, so there is no propagation delay issue what we saw here. So this issue has been eliminated here. Okay, now let me just repeat it. When the clock is low, this node gets charged to 1, this gets, because it is an inverter, this gets charged to 0, right? So this is node gets to charge. So when the clock is going high, so this is 0 here, so this 1 continues to remain 1, there is no issue at all. Okay, so there is nothing is is going to happen here, and this output is going to be 0. Now if the input is suppose the input is such that this output is to be discharged to 0, in that case this will be discharged to 0, then this will go to 1, and if this goes 1, this goes to 0, and this goes to 0, this goes to 1. So this is known as a domino effect, right? What is a domino effect? You see a lot of you keep seeing in movies and all, and the cards are placed vertical, and you just push one, and then the whole thing which is lined up, they fall one after the other, right? So it is like that. If this is going high, then this goes low, then this goes high, so this domino effect propagates. So this is known as domino logic. I have implemented this thing, the adder which we discussed in the last class, now using domino logic. Now if you see here, this was the pull down network for carry, right? So the entire PMOS network has been removed, and I have just put one PMOS here, and I am providing a clock there, and I have introduced one more NMOS here. So these are this 1 2 3 4 5, right? This is the carry generation. So I have the entire corresponding P network has been, pull up network has been removed, and I have just put a single PMOS out here, right? And then this is carry bar which gets generated. You just have to refer your previous class where we discussed about the full adder. So this is the same full adder which we discussed, a 28 transistor full adder which we discussed in the last class. Now we have modified it for domino operation. So you see that entire P network, if you see here, this entire P network has now been replaced with a single PMOS here, right? And then this is carry, and then I'm putting one more inverter to get a carry now. So this is a domino logic, and also I am putting a weak PMOS here after the inverter. Now this carry, this is the inverter which we are using here. This is to avoid the charge sharing problem. Now I am using here a carry to the sum module. Again, this is the sum. Only the N network has been used here. The entire P network has been removed in this particular case, if you see here, and replaced by a single PMOS out here. And then you have the sum inverter, and from the output of the sum inverter you have a weak PMOS which is driving this. Okay, so this is the theory behind the domino logic. Okay, let me stop this presentation here, and then let me show you the demonstration now. Okay, so this is what we have implemented in LT-SPICE. So all these things, how to import these libraries, these things we have learnt in our previous class. Now if you see here, I am giving a clock to this PMOS, clock to this NMOS, clock to this NMOS, and PMOS. So there are top and bottom. There are these clock enable PMOS and NMOS have been put. So this is the keeper. Now for the keeper, if you see here, I have put the length as 1800. This is the minimum width, but I am keeping it a length also, so that to make it as weak as possible. So this is 1800 nano and 400 nano. For 180 nanometer I can't decrease the width below 400 nano. So now instead of decreasing the width, I have kept the width at minimum possible and increase the length. Okay, now if you see, the same thing I have done here. Whereas for this PMOS, again I told you it can be a PMOS with minimum width. Okay, so there is no need of having a big PMOS and adding unnecessarily stray capacitances. So I have just used a 400 nano minimum width possible. So here also I have used a 400 nano. Whereas these NMOS have been sized so that it can pull down. So wherever there is only 2, I have used 400, and here it is like 800 nano. This we saw in the last. This NMOS, the sizing remains as same as that of 28 transistor which we saw in the last class. Now if you see, there are 3 signals out here, and there is one clock signal. So let me run the simulation first. Okay, and then let me plot the clock first, and then plot A, B and C, and then let me plot sum, and then carry. add plot B. Let me take the clock first. A, B, C, now if you see, when the clock is high, the sum and the carry they are slave to 0, because previous stage it is been, if you see the diagram, clock bar and the sum bar are pre-charged to 1. So obviously carry and sum will be pre-charged to 0. So whenever the clock is 0, the sum and this is 0. And when the clock is high, so here you have A, B, C all 0. So sum and carry both 0. Again the clock is 0, they are being pre-charged to 0. But when the clock is high, this is 1 and this is 0. So the output is going to 1. Sum is going to 1. In the next clock, when it is going high, you will find this is 1, right? And sum is 1. And this also, it is again getting charged to 1. Here you will find that this was 1 out here, but when the clock is 0, it is getting pre-charged to 0. So it is getting pre-charged. So only valid output will be available when the clock is high. Whenever the clock is 0, you will find everything is 0. Okay, outputs are 0, 0. So in the next combination, you will find 1 and 1 here. Both are 1. There are 2 ones here when the clock is high. So you will find carry is 1 and sum is 0. Okay. So next combination, if you see clock is 1 here, you have 0, 0, 1. So sum is 1. Next clock high, you have 1, 0, 1. So you have 0 and clock 1. And when the next clock is high, you have 0, 1, 1. So 0, clock 1. And then the last combination, you have all the 3 ones. So you have the sum 1 as well as carry 1. So you see here, whenever the clock is low, these are getting pre-charged to 0. The sum and carry are pre-charged to 0, and whereas when the clock is high, you are getting the correct output. Okay, I can even plot the carry bar and the sum bar. If I do that, carry bar and sum bar. Okay, so it is just inverse of carry and sum. Only thing is, these nodes, carry bar and the sum bar, whenever the clock is 0, they are getting a pre-charge to 1. So whenever the clock is 0, you can see that whenever the clock is 0, these are going to be get pre-charged. So because if you see here, this is the PMOS. So whenever the clock is 0, these nodes will be pre-charged to 1, and carry and sum will be pre-charged to 0. So that is the only difference. So if you see here, now you can, if you want to find out, what you can do is you can do an power analysis. You have already done the static design. Now if you see here, a lot of it will be faster also, because the capacitance associated here is less. First of all, there is no rise time here. Okay, the 1 will be readily available. So there is, you can say there is no delay for 1 also, whereas in the static design, some time will be required for the output to go to 1 here. So here there is rise time is 0 in one advantage. Second advantage, the fall time will be much faster. Why will it be much faster? Because the node capacitance here is much lesser. The entire PMOS network is not there. So this node will come to 0 at a much faster rate than it would happen for a static design. So it is faster. The power also will be lesser. So what you can do is if you have already simulated the static CMOS design, you can do the simulation here. And in the first class, I guess we learned how to do the power measurement and delay measurements. So you can make a table and compare the power, delay, area, these things. These are all the figure of merits. So you can compare all these figure of merits, and you will find that dynamic full adder, or this is in fact a domino full adder, is much better in terms of area, power and delay than the static design. Okay, so that's all for today. And also, as an home assignment, you can try out making flip-flops. Okay, a D latch I had discussed in the last class, and I have showed you a small demo of how to design a D flip-flop. So you can read your textbooks, or you can Google using master slave flip-flops. You can make master slave latches. You can make by using 2 latches as a master and a slave, you can make D flip-flop. Okay, only thing is a complementary clock is to be given here. So in this particular class we have learned how to give the clock also, right? So you can do the same thing using the same type of clock and a complementary clock, and you can try to implement an D flip-flop. And in case you are getting stuck, feel free to mail me on that aspect. Okay, thanks a lot.